Hello, today we are going to be continuing our sum and difference properties. So there's a lot of different applications where we can use those composite argument, the sum and difference properties, in order to help us find exact values. So we're going to ask, how do I find exact values of angles not on the unit circle? So if you remember, before we could only do things that were special right triangles, 45, 45, 90s, or 30, 60, 90s. Now we're going to talk about how could you find those exact values without using a calculator and actually getting a numerical value for it. So let us begin. Remember, you're going to want that formula chart out next to you. So on number 1, sine A equals 1/2, and the cosine of A is greater than 0, and tangent of B equals 3/4, and sine of B is less than 0. So on these types of problems, they're going to ask you to find the exact value of A minus B, or sine of A minus B, or the sine of A plus B, etc., etc. And so really what the goal here is if you can draw the pictures. Okay, we're going to be drawing some more triangles in here in order to use these properties. So the first thing we've got to figure out is what quadrant each of these are in. So this sine is positive, and then this cosine, if it's greater than 0, that also means it's positive. So if I look at my all students take calculus, if I have positive sine, positive cosine, that means I am in quadrant 1. Okay, similarly, if I am looking at tangent of B, this is a positive value for tangent, and then sine is less than 0, so it's a negative number. So I want to know, where is tangent positive? Well, it's positive in 1 and 3, but we also need sine to be negative, and so sine is negative down here in quadrant 3. So now I know where to draw my triangles. Let's go ahead and do that. So for the first one, for A, we're going to draw it in quadrant 1. So this is angle A. And I know, using SOHCAHTOA, so if you need to remind yourself, we have SOHCAHTOA, that the sine is the opposite over the hypotenuse. Once I use my Pythagorean theorem, I can find that this other side is √3, or you recognize that this is a 30, 60, 90. Okay, so now at this point, I can also draw my tangent, my angle B, and so that one is going to be in quadrant 3. And you can put these on the same unit, or on the same circle, that's fine, or same coordinate plane. I'm just showing this differently. Okay, so this is angle B over here. I have that the tangent is 3/4, so the opposite over the adjacent is 3/4. Now be careful here though, because this is in quadrant 3, this one's negative because it's going down, and this one's negative because it's going to the left. So then I can use my Pythagorean theorem again. 3 squared plus 4 squared is going to get me 5 squared, and so I have a 3, 4, 5 triangle. At this point, I can use my sum and difference properties using that formula chart. So if I look at sine of A minus B on my formula chart, I would have sine of A times cosine of B minus the cosine of A times the sine of B. Okay, so that is the equivalent for that composite argument. And now all I have to do is take the values from my unit circle. So the sine of A, the opposite over the hypotenuse, is just 1/2. The cosine of B, of angle B, is going to be the adjacent over the hypotenuse. Okay, then I'm going to do the same thing. I'm going to have a minus sign in between them. And then we have the cosine of A, so I would have √3 over the hypotenuse is 2. And finally, the sine of B is the opposite over the hypotenuse. Okay, so now I have exact values for those pieces, and then I'm going to go ahead and just simplify where I can. And so this, if I time straight across, I get -4/10 minus, we would have a negative times a negative, so this guy actually turns into a plus. So 3 times the square root of 3 all over 10. If you notice here, I have common denominators, how nice of them, and I'm going to have -4 plus 3√3 all over 10, and that is my exact value. This is not a decimal approximation. We leave it alone and keep that radical in there, and all we did was draw the pictures and then use the property. Okay, the next example we're going to see is finding an exact value, again, of an angle that's not on the unit circle of 15 degrees. Now, these can get really tricky if you overthink them. what you're going to do here is try to think about, how could I get 15 degrees knowing the angles that I know? So for instance, we are looking to make this into terms of 30, 60, 90, or 45, 45, 90. If I can make this using a composite argument, using those special angles, then I can actually find the exact values of the pieces. Okay, so if I remember that I know 45 and 30, and if I take that and subtract it, that would get me 15 degrees. And now this is a composite argument. So again, if they asked you for like the sine of 75 degrees, you could just do 45 plus 30. If they asked you for anything like that, just figure out how you can make your argument into a subtraction or addition problem. So now at this point, I can use that same property that we just used, the sine of a minus b, and I can plug in this for a, 45 for a, and 30 for b. So I would have the sine of 45 times the cosine of 30 minus the cosine of 45 times the sine of 30. And again, these are values that you should know. They're on your unit circle, or you could just draw out your triangles and find them. Okay, sine of 45 degrees is 1 over root 2, or square root of 2 over 2. The cosine of 30 degrees would be adjacent over hypotenuse, so that would be root 3 over 2, minus the cosine of 45 degrees is 1 over root 2 as well. And then the sine of 30 degrees, we would have the opposite over the hypotenuse, so 1 over 2. Again, these are just exact values. We've just broken it down. Now I can simplify this, so I would time straight across. I get root 3 over 2 root 2 minus 1 over 2 root 2. And then I can just write that as one giant fraction. So root 3 minus 1, or negative 1 plus root 3, all over 2 root 2. Okay, and so that's how you'd find a regular trig value using that. Now, if you were given cosecant of 15, I could try to rewrite that using a composite argument. However, I don't have any sum and difference properties for cosecant. So you're going to have to remember your reciprocal identities, which, remember, are on your formula chart. So cosecant is equal to 1 over sine of that argument, and we just found that. Okay, we found over here that the sine of 15 degrees is this exact value. So all I have to do is flip it over, or do 1 over. So I would have 2 root 2 over root 3 minus 1. Okay, and now we could do cosine of 75 degrees the same way. We could go through here, and I could find the cosine of 30 is one of the angles I know, plus 45, and then I could do all of that composite argument stuff again. However, we have a rule called the cofunction property. And cofunction properties say that the cosine of something, if I take 90 minus the complement of that angle, it's going to get you the sine of 90 minus that. Okay, and so with the cofunction, I wrote mine in the opposite order. I'm looking at my formula chart incorrectly. If I want to find the cosine of 75 degrees, I can just find the cofunction, so the sine of 90 minus 75, and we already found the sine of 15 degrees. Okay, we already found it over here. And so if you work smart, not hard, you would know that this is exactly the same. So again, if you're looking at these types of problems, if you recognize a cofunction in here, which would be 90 minus whatever angle, we already found that sine of 15, so the cosine of that cofunction of 90 minus is just going to be the same thing. Okay, so I will see you on Monday. Have a great weekend.